Can everyone hear me fine?
I can hear you well.
Okay, great.
Okay.
So I'm really excited to introduce my advisor, Skyler Cranmer. Skyler is the Carter Phillips and Sue Henry Associate Professor, or full professor now, of political science at Ohio State University. Skyler has introduced a ton of machine learning and network science approaches to political scientists, and he's trained a bunch of different assistants and associate professors across the discipline and has like a heavy influence in our field. So I'm so excited to see his presentation today.
Oh, well, thanks, Jared. This is actually mostly stuff you've seen from me before, but hopefully this will be useful for everyone else. So thank you all for coming. I really appreciate it. And sorry for the AV problems. I think what you're seeing on my screen is the entirety of my screen. So that means that I'm not seeing you. So if you have a question, please speak up. Because I can hear you, but I can't see anything other than my slides right now. Yeah, basically, should I just take it away, Carl and Peter, or did you have something else you wanted to do procedurally before we start?
Oh, no, we just need to formally introduce now that welcome, and also welcome to the colloquium and data analytics colloquium. Peter, do you have anything to say before Dr. Cranmer takes on?
Yeah, just briefly, just want to introduce this data analytic colloquium to all the audience. Briefly, introduction, because we started this initiative like 3 years ago, and this is the 3rd year actually. And we're excited to have more and more well-known scholars and introducing the up-to-date or top-notch scholars introducing their research. So we're excited today, and then we have Dr. Cranmer and Dr. Jordan. And so this is really our honor. And please, I think there's new friends and old friends from Taiwan and from the United States. And then I think this is quite a new. It's a new trial. Let me put it this way. And Carl and I put this together, and with advice from Dr. Aiken and the late Dr. No, whenever I that's
Harold Clark and Dr. Shi Yan.
Yeah, I know. It's Dr. Clark, because I have to put my emotion away though. And then so with their help, and then we set up this colloquium, and we want to try to introduce all these new techniques or methods to our students. So most of our audience or participants are students from both sides. Part of the audience from Carl's students, and part of it is from my students, and most of them, they are master students. So we're really excited and to learn new things and more things. So just I want to pass this mic to Carl, and let's proceed this colloquium. And today I think this is quite special because it's more like the workshop type. So we can actually see Dr. Cranmer showcase this how to do this network analytics. So let's hold on, sit tight, buckle up, and then see what we'll learn today. Thank you.
All right. Thank you again, Dr. Cranmer, and without further ado, and please.
Okay, thank you, and please call me Skyler. Only undergrads call me Dr. Cranmer. Okay. Yeah, today it's going to be a pleasure to talk to you a bit about inferential network analysis. And I'm approaching this, I hope correctly, from the idea that most of you have not really seen networks before, let alone done descriptive network analysis, let alone inferential network analysis. Is that approximately right?
Mostly, and we have some students and taking one course before from one of our professors, and actually Jared also presents something when he gave his talk here, and that really get us exposed to the start of some simple ERGM models, and we really look forward to to you to give us a really good introduction and also more latest development.
Okay, great. So my plan is to basically start from the concept of what is a network, what do the data look like, what are the sort of design and data gathering challenges that go along with network analysis, and then get into why we need special techniques to do this, and then show you one of those techniques, which is the ERGM. But there are others. So this is just the tiny tip of the iceberg. Normally, I teach a full semester class on this, and my co-authors and I recently just published a book with Cambridge Press called Inferential Network Analysis that goes through all of this in much more detail. So since we only have 2 hours together, this is going to be a very high-level overview of some of this stuff, and we'll only touch on one of several possible techniques and approaches. So with that, I guess we'll get into it. Network science and network analysis is a little bit different than the traditional rectangular analysis that most people are used to seeing, where we have a dependent variable that is a list of observations, so one observation for each unit, and then several covariates on that. It comes at things from a slightly different perspective. And the perspective is that connection between actors or between entities is fundamentally important. And that in complex social systems, where we have lots of interactions and influences that go from one unit to the other and form complex patterns, there's a network that underlies all of these connections and actually governs how the systems evolve, organize, and adapt. And so in that sense, networks are really important because they're the structures that define the interactions between whatever units we're studying, whether those are people or institutions or countries or whatever. So the perspective that we come at things from is that connection is fundamentally important, and we want to be able to study the way that units connect with one another. And so to give you a little idea, or a first idea of what a network is, first I need to introduce a little bit of terminology. In network analysis, it's sort of plagued by two sets of terminology that mean the same thing but come from different places. So there's a set of terminology that grew up in the social sciences and another that grew up in the mathematical sciences, especially math and physics. And so a mathematician would call a network a graph, whereas a political scientist or sociologist would probably call it a network. And a network is composed of two basic things, which we can call nodes or vertices if we're going to use the physics math lingo. The nodes are the actors or the entities that are interacting with one another. So those could be countries, like in the network we're seeing below, or they could be relations. Or they could be, anything, actors, right? The node is the thing that is doing the interacting, and the relationship or the edge that's defined between them is the relationship between those things. And so in this example network, this is transnational terrorism from 1988. We see that the nodes represented as dots here are countries, and the relationship between them is directed in this case. So it goes from one country to another and implies, in this particular case, that someone from that country committed a terrorist attack in the other country. So if you can see up top here, someone from Panama attacked a target in Costa Rica, and someone from Colombia attacked a target in Venezuela, and a different someone from Colombia attacked a target in Ecuador. And so those are sort of simple and easy to see, but we also see down here that there's much more complex structure at work in this network. And modeling that sort of structure is the main goal in a lot of ways of inferential network analysis, but we'll get into that a little bit more as we move on. Oh, and the other thing to know is, as someone who teaches statistics, it makes me nervous if no one asks questions. So if you have a question, please just speak up as soon as you have it. Like, there's no need to raise your hand or anything like that, especially since I can't see you. So just shout out, and happy to take the question. Okay, so finishing with terminology, we talked a little bit about what nodes are, but this is a sort of more formal treatment of them. They're the actors that are in the network. They can also be called vertices. Where it gets a little more complicated is when we're talking about the relations. So these are called relational ties or ties, and ties span a dyad. So a dyad is an important piece of lingo in networks, because a dyad represents the relationship or lack of relationship between a pair of nodes, so a pair of actors. For example, any two countries in the international system will have a dyad. That doesn't mean that they have a relationship. It's the potential of a relationship is what a dyad captures. So a dyad is just a pair, and that pair can be connected or it can be not connected, or it can have a valued connection or a whole bunch of other things. And without throwing too much terminology at you, basically, we can think of the edges as these connections, these links between the actors, and that can be simply on or off. So 0, 1, like we're friends or we're not. It can be directed. So I think you're my friend, but you actually might not think that I'm your friend. So it's a directional tie that can go both ways, but might only go one way, is what we mean when we say a directed network. And that's what this picture I showed you is. This is a directed network because it's someone from one country attacking a target in a different country. So there's directionality there. So that's a directed network. The connections can also have what are called weights, which is like a quantitative value. So maybe we're talking about international trade and how much money goes in trade flows from one country to another. So that would be both directed and weighted in that case. Or it could have qualitative attributes, like the connection is strong, very strong, or weak, something like that. Does that make sense as the basic kind of terminology that I'm going to be using throughout this
yes.
presentation?
Yeah.
Great.
Thank you.
Okay, so a couple other bits of terminology that we need before the rest of this is going to make sense. I talked about what dyads are. That's a pair of actors, a pair of nodes. A triad is a different sort of what are called subgraphs. And yeah, so if the network as a whole can be called a graph, then a subgraph is some sub-element of the network that's a subnetwork. But confusingly, in the social sciences, we tend to call the entire network the network, and we call the subgraph, even though we're now mixing terminology from math physics with more social science terminology. So this can get a little bit confusing, and people also tend to say nodes and edges, where it should really be vertices and edges or nodes and links. But people mix and match those, and I will probably do that accidentally just as we're going on. So it's a little bit of a lot of terminology, but hopefully this is making sense. So in terms of subgraphs, some sub-elements of the big network, the dyad is the most basic pair because it's only two actors, so only two nodes. The triad is a set of three nodes and the relationships among them, and any other subgroup or subgraph can be defined of any size, right? So we could have a subgraph of 4 or 5, of 6, of 7, of 8, of 9, of 10, just whatever. And so the concept of a subgraph is going to be important when we talk about how to model endogenous structure in networks. So that may seem kind of not relevant at the beginning, but I promise by the end of the workshop, this is going to be an important concept. Okay, so something I want to mention, but then not talk about, is the possibility of multi-mode networks. So a multi-mode network is a network that's composed of two different types of nodes. So we could have, I tend to draw on international relations as an example because that's the subfield that I'm best trained in and most published in. If we're talking about countries as the blue nodes and maybe treaties or international organizations as the red nodes, then a two-mode network is how countries tie into those organizations. And so we have two different types of nodes in the network. That can be people linking to something else, right? People linking to companies or something like that. Yeah, so this exists. There are ways to do inference on this, but we don't have even close to enough time to dig into that today in this sort of intro session. Just know that it exists, and if you're interested in networks that have two modes, there are resources you can learn about it, and it's by no means a barrier to doing inferential network analysis.
Mm-hmm. Quick question,
yeah.
Skyler. So in your previous chart, it suggests that the unit of analysis can be more than one. I mean, one type, right? So the blue dots are the unit of those are the country. So the red dot is of a different unit of analysis, right?
Yeah.
So
yes,
So in terms of the data, is this tabular data or it will be tying to like a relational database?
Yeah, the way it's usually organized is in terms of adjacency matrices. Though with a two-mode network, it looks a little bit different because you have basically a edge list of the actors and the other types of the other type of mode that they tie to. So to be very general about that, right? You have a list of one sort of mode and the other sort of mode, and an edge list of how they connect. But it's not actually a problem to have two different sorts of nodes in a network.
Yeah. Okay.
And maybe we can actually generate some examples. So I'm curious to hear from you all what sort of phenomena you're interested in that could be thought of as networks. Does someone have an example of something that they're interested in or are working on? And please speak up again because I can't see you.
How about social media?
How about what?
Social media data or we have some other question too. Go ahead.
Oh no, I'm not having a question yet, but I would like to share. Like I'm looking at the social media data as well, and I'm trying to see the network, how people, like the whole community, communicate with each other in the outbreak of COVID-19, especially when the whole country it experienced food insecurity issues. So I'm trying to see like the role of nonprofit in that whole community networks there.
Okay, so that might be actually a two-mode network in terms of people on a platform like Twitter, for example, individuals tying to organizations. So you could think of that as a single mode network if we're just treating every Twitter account as a node. But if what you're interested in is specifically how people interact with the institutions that came into play around COVID-19, then maybe it would be more theoretically appropriate to treat it actually as two modes of individuals tying to institutions. So yeah, that's a really good example.
Yeah.
Does anyone else have an example that they're interested in?
Anyone?
Well, that's okay, because I have examples. So here's one of the examples that actually first got me interested in network analysis way back in the day. So my first exposure to network analysis was not long after 9/11, actually. And this, I think, is an interesting portrayal of what the 9/11 hijackers network looked like. So here the nodes are people. The relations between them are weighted by how strong the connection is. So we have thicker lines for people who knew each other better, and thinner lines when the relationship was more weak. And they're colored by what airplane they hijacked. And the nodes in gray were associates, but not actually hijackers. And so in principle, if one could understand a structure like this, one would have a better chance of disrupting it before the fact. And there's a lot of interesting network analysis that goes into that in terms of seeing how networks can be most disrupted by some sort of enforcement activity. So that's one example.
Yeah. We have one more question too. How about using one guest suggested as a, how about event data as an example? Can you try to think about the event data like conflict events or repression events? Can that be analyzed in networks?
Maybe. So that's just that's like one component, right? So what we would need to know in order to turn this into a network, if we wanted to do that, was what actors are involved in the events, and how they're interacting with each other, or how the events interact with one another if they do. But if it's just a list of events, that's not necessarily a network. Where a network emerges is when we have a structure of connection between units. So if the units are events, then the question would be, what is the structure of connectivity between those units? And if we're assuming that these are independent events, then there probably isn't one. So maybe that's not a network, or maybe maybe we have information on what actors are involved in the various events. In which case, then it could become potentially a network. The main thing is we don't want to create networks where they don't need to exist, because it makes our life a lot harder. But oftentimes we're led to situations where the network basically has to exist.
Yeah. One member also asked a question about transatlantic drug trade. Can that be a good example? Or
yeah,
like
if you have information on what countries are shipping what to whom, then that's definitely a network.
Yeah.
So you probably have sender countries that are exporting drugs, and receiver countries that are importing drugs, and then the connections would be either the type of drug or the amount of the drug or something like that.
Yeah.
But yeah, that could definitely be a network.
Jared just posted an example like a civil conflict battles to track the movement of rebel groups. I think that could be a good example too, right?
Yeah, there's a paper by Shahryar Menas and some of his collaborators that do a fairly similar thing to that using Nigerian conflict data, which is a cool paper, looking at the interactions of different rebel groups.
Yeah. Yeah. I think, sorry, please proceed with your next example. I think I interrupted. Yeah.
Oh, no, that's fine. That's good. So please do interrupt as soon as people have questions.
Okay.
So this is just one other example. This is a two-mode network from bayrule.net, which is looking at corporate board membership. This is specifically in Bay Area companies, but they have it for other companies too. So this is, for example, the corporate board for Wells Fargo, and these are the people who are on that board. And some of those people, like this guy, Richard Kovacic, is on the Wells Fargo board, but also on the board of Target and also on the board of Cisco. So he's on 3 different boards, and then he's connected to Dwight Powell, who's on the board of Applied Materials, and also connected through one degree to John Hennessy, who's on Google, as well as Cisco. And so you can see the relations multiplying this way, and you can track relationships through this network. So this is an example, again, of a two-mode network. This is people connecting to corporate boards. Here's a really famous example of Facebook. So people are Facebook friends with one another, and that's the connection. So the nodes are the individuals, the accounts, and the edges are the connections in terms of being Facebook friends with one another. And we can draw quite a nice map of the world that way, except for Russia and China, as you kind of notice. But yeah, so that's one example. We can also think about transportation networks. So the road network that transports goods, services, and people. Brownie points to anyone who can guess what city this is. Hint is that all this
California?
is train, and that's a big central train station right in the middle of the city as the river forks around it and a lake.
This is on the East Coast or west?
Neither. This is in Europe because American cities don't have central train stations.
I was thinking about what Washington DC, but
yeah, no, this is Zurich, Switzerland.
Zurich. Oh,
yeah, with the central train station right there on the Lake of Zurich, and then the river that runs eventually to the Rhine. Okay, so that's one example. Examples abound. Here's another two-mode network of. This is a particularly fun data set if people want to do some exploratory network analysis. It's called dirtymoney.org, and it shows American legislators as one sort of node, and then the corporations that give them money as the other sort of mode, and how they connect. So Chevron is giving, I can't see who that person is, but Chevron's giving a bunch to that person and also to this person, and then less money to that person and this person. But yeah, you can basically track who the corporate sponsors of American politicians are, and it's an interesting data set to explore. But to bring it back to the anatomy of networks, we've talked extensively now about vertices, about edges, about dyads. We haven't mentioned loops, but that's a tie to oneself. So sometimes that makes sense and sometimes it doesn't. But in certain contexts, it is possible to have a relationship with yourself that is as meaningful as a relationship with someone else, depending on what it is that we're measuring. We talked about how the edges can be directed or undirected, so it may be something going from me to you, or it may just be undirected, which is that a connection exists or it doesn't. So two students who are in a class together, they have an undirected connection. You're either in the same class together or you're not, versus being friends or lending each other money or something would be a directed network. So if a network is directed, it's not necessarily true that Nij is equal to Nji. And this is an important bit of notation as we start to build up to doing some math. We refer to the network as N, and the actors involved as I and J usually, or I and J and K. So Nij is the connection from node I to node J in the network N. And Nji is the connection from node J to node I. So if a network is undirected, these are going to be the same thing. So if it's a 1 from I to J, it will be a 1 from J to I. If it's an undirected network, but if it's a directed network, it's not necessarily true that those things are equal, right? If I'm I and you're J, I may think that that you're my friend, but you may not think that about me. And interestingly, if you do friendship network surveys, asymmetric friendships are very common. So someone nominates someone else as a friend but doesn't get nominated. So one more thing to feel insecure about. Okay, so yeah, we talked about that, and yeah, we also talked about multimode networks, which can also be called bipartite or multipartite. But let's get a little bit deeper into the math of this. This will be important later. We say that there are small n nodes in big N network. So big N represents the network, small n represents the number of nodes in that network. There are n choose 2 possible edges, so possible relationships in a graph. If n is undirected, meaning a relationship is either on or off, and there's 2 times n choose 2 possible edges if it's directed. And that means that this adds up pretty quickly. So if we had 100 nodes, that's a little bit shy of 5,000 possible edges that exist among those 100 actors or 100 things that are the nodes. So how do we store these networks? We're not going to do a whole lot of data wrangling today, but it is worth pointing out that the shape of these data sets is usually pretty different than what we're used to for like a regression. A very typical way that network data are stored is in what's called an adjacency matrix. And technically that only refers to a matrix of zeros and ones where connections are either on or off, but we use it kind of loosely to mean any sort of relational matrix. So a relational matrix must be square. So if we're again thinking about countries like the US, the UK, and France, it's US, UK, France on yeah, what we would call the Y dimension and also on the X dimension. So that creates a matrix that is necessarily going to be square. And in this case, we have NAs down the main diagonal because, well, actually, I don't have a specific example in mind here, but we're just assuming that loops are not possible. So, so it wouldn't make sense to fill that in. But if loops are possible, then this could also have values here. But what this means is that the relationship that the UK has to the US is 0. And also the relationship that the US has to the UK is 0. The relationship that France has to the UK is 1. And the relationship that the UK has to France is also 1. So in this case, we have a symmetric matrix, which would imply that it's undirected. But if it's a directed matrix, this doesn't necessarily have to be symmetric along that main diagonal. Does that make sense?
Yes.
Okay, great. And that's a very typical way that network data are stored. The other main way that they're stored is in what's called an edge list, which is just a list of all edges. It would be, it would not necessarily list edges that don't occur, but it would list edges that do occur. So an edge list would look like UK FR, and then the next line is FR UK, and it would pick up on that. And then by implication, anything that wasn't listed as an edge is not an edge. So that's another way that you often see network data stored. But what makes it even more interesting is that in addition to having that relational component, so the main component of the network being the relations, we can also have node attributes. So it's very common, again, for example, in international relations, that we have a lot of information about the given countries. So we know, for example, the GDPs of countries or their crime rates or whatever you might want to know about them measured at the country level, even if the main thing that we're interested in our analysis is the relationships between countries. These individual vertex level factors can matter, and these are called compositional variables. And one of the neat things about the ERGM that I'm going to introduce a little bit later is that it can deal with compositional variables that are measured at the actor level, at the relationship level, and then it can also include broader endogenous structures all in the same model, which is something that we really can't do with regression. So it also opens up new theoretical horizons for us in terms of integrating multiple units of analysis. And that's kind of cool, I think, at least. Okay, So we will very often have compositional variables about either the actors or the relationships between them, or both. So that's sort of the blitz introduction to what network data look like. Does that make sense?
Yeah.
Okay. So the next thing that I want to cover briefly is elements of designing a network study. Sometimes one can just go out and grab a network data set, and that's usually useful for learning how to do these techniques. But if you're doing original research, you usually need to approach data collection the same way, largely the same way that you would in any other study, meaning thinking about things like sampling and bias and all of that. And it can work a little bit differently, and networks introduce some interesting complications in this respect. So if we start walking through the process of designing a network study, step one, as it is also with regression analysis, is to define the population. So what's the population of cases that we're interested in studying? Is it possible then in step two, when we think about sampling that population, do we need to sample it? Can we get a census, meaning gather information on all of those observations? If we're talking about international relations, it's often possible to do a census because there aren't that many countries, and we can often get information on how all of them relate to one another. But if we're talking about, say, people in the world, it would be not possible to get the complete social network of the world. So some sort of sampling scheme is going to be necessary. And this is where you start seeing some real non-trivial challenges to doing network analysis, and specifically to gathering network data when you're not able to do a census of the network. Because you have sort of two main options, and there are variations on these, so don't take that to be exclusive, but two of the most common options that people will go with is that they can either do a simple random sample. And so let's say we're doing, well, let's say I'm in Columbus, Ohio right now. So if I did a simple random sample of people in Columbus, Ohio, and I pull 100 people, the chance of any two of them knowing each other is going to be really rare, right? So I'm going to get 100 people who probably don't know each other, and I'm going to ask them about their friendships. And that's going to create what's called an ego net. So the ego net is the person who you sample is the ego. And then we have a little network of who they know. So maybe that person has 5 friends, and we then have 5 relationships from that ego to those friends. But we don't know if the friends know each other, and we don't know who else those friends know, which is a limitation of that sort of random sampling. And so you may say, well, maybe it's better to do what's called snowball sampling. And snowball sampling, you might start it multiple times, but just to make the example simple, let's say we only pick one seed node. So we pick a person in Columbus, and we say, okay, I'm going to take that person, ask them about who they know. So now I get that ego net of who they know, but then I'm going to go find their friends. So all the people who they nominate as friends, I'm going to talk to them, get them to nominate friends. And so now it goes out by 1 degree. Then we're going to get all of those people and ask them who their friends are, and so on and so forth. So every time we go out by a degree, the magnitude of the sample increases non-linearly usually. And it also provides us with interesting complex data, because even within 1 degree, once we go out that 1 degree, we'll know whether the friends of the original ego know each other, right? They may nominate each other as friends, or they may not. And so that's how snowball sampling works. Does that make sense as a concept?
Yeah.
So snowball sampling is a good way to approach things if you have a relatively small, relatively well-contained population. But even then, it's usually going to be pretty expensive. Like this is hard to do. It takes a lot of time and often a lot of money. And you have a problem, which is where do you stop? So how many degrees do you need to go out before you have the network? And that gets back then to that first question of what is the population? So if I'm trying to get the social network of Columbus, that sort of gives me a stopping point, right? If we're talking about people who are outside of Columbus, because many people have friends who don't live in the city, that's then the sort of boundary. And that's where I stop sampling. But sometimes it's also not so clear. So, for example, snowball sampling has been used extensively to study the habits of IV drug users, mostly heroin addicts, and especially because they're a hard population to sample. Like if you just did a random sample of people, you probably wouldn't get many or any heroin addicts in the sample. So the way they do this is they'll usually start at a treatment clinic, recruit subjects there, and then snowball sample out. But then the question is, when do you stop? Because that network actually keeps going and going and could eventually span the globe, right? So there's not necessarily a natural stopping condition. Maybe you define it by city or by state or by some sort of municipality, but you would need to think about what the stopping conditions are when you go to gather such data. And that makes gathering these sort of data often really difficult. Does that make sense as sort of a design problem that we often encounter?
Sure, yeah. Mm.
Okay, great. So then usual rules of design apply. We need to think carefully about data collection. How are we going to do it? Is this a questionnaire? Is it archival? Is it observation? Is it an experiment? We need to worry about things like accuracy, validity, and reliability, and all sorts of measurement error. Like you're not exempt from any of those things that go along with normal data gathering when you're doing this on the network. It's just often harder because of the sampling problems that we were talking about. Okay, so yeah. Someone remind me what one of the examples was. I know someone was interested in drug trafficking, right?
Yeah. Yeah.
Oh, go ahead.
Transatlantic drug trade, like crossing Europe and US, I think, America and Europe.
Mm-hmm. So I guess the first thing, if we think about that from a design perspective, is defining the population. Why specifically transatlantic and not trans-Pacific or within a continent or something like that? What's special about the transatlantic bit? And do we need to consider broadening that population? Or is there a theoretical reason to keep it limited specifically to transatlantic? So defining the population is a non-trivial part of getting the sampling and data collection right for that. And then comes the really hard part, which is how are you going to actually sample this? Is it possible to get information on how every country trades drugs with every other country? I don't know the answer. I'm hoping the person who's interested in this does. How actually, to that person, how are you thinking about gathering these data? Or do you
Maybe
already?
I can check with Daniela if you have follow-up question and about this and about the design, and then you can either speak up or you want to type it in the box. I can do that for you. I have one follow-up question. For example, I want to look at the event data, and we have a professor here, Dr. Patrick Brandt, and is collecting the event data by the cameo codes. So these cameo codes represent the dyadic or a triadic or maybe multilateral interactions. For example, I'm most interested about Taiwan, US, and China, for example. And then China say something, then US response, and Taiwan response. And so that could be just like a three node network to start with, but it could be something spilling over to other nodes like Hong Kong and maybe ASEAN countries, Japan. So how do we put this in? I know that the cameo codes could represent different events or different interactions, and so the edge or the link in this case could be just like a one-dimensional, right? Just the size of, or maybe a size of the tray or exchanges. And but what if you have some intensity or with different types of contention?
Yeah, so if you're looking at something like cameo codes, which reflect or can reflect the relationships between countries, that could be like a hostile statement from China to Taiwan and a supportive statement from the US to Taiwan or something like that. So that would imply a weighted connection and also a directed connection. In that case, if you have only the three nodes, let's say US, China, Taiwan, that may be all you need, in which case it's a pretty straightforward network in the sense that with three nodes, there's not much room for network structure, right? Where network structure really raises its head is when we have more complex networks like the one we were looking at before, like here, right? We have a lot of complex structure happening in there. And so if we only had three vertices, it would necessarily be simpler and maybe a little bit overkill to do a full like ERGM network analysis there. But if we're thinking about how countries interact with each other, either in Asia or Trans-Pacific, or maybe even more broadly internationally, then there's room for a whole lot of complex structure there, because how the US, China, and Taiwan interact probably also conditions how China interacts with other countries in the region. And that's where we can see that sort of structure coming out. And we can learn to leverage that structure in order to learn more about the process. Does that answer your question?
Yes, it is illuminating. I'm thinking about, for example, the COVID network, and about, I mean, the vaccine network that US, China, Taiwan, and Japan, then later there's some European countries, and helping Taiwan, donating vaccines, and just last year. So that will be seeing some. It's not just a trilateral relationship, and you can see that the other countries' responses to this could be conditioned by one of these nodes or these players. Yeah.
There's room for a lot of complexity there, actually. Cool. So so actually defining that population is non-trivial, in fact, right? Because you could think, it's the narrow definition of that might just be US, China, Taiwan, but then the bigger definition could include a whole lot more countries. So having theoretical motivation behind that definition of what the population of interest is really important there. Okay, so what do we do with networks? There's a whole lot that we can do with networks. Network theory is a whole area in and of itself, basically about how the structure of networks can come to produce more than the sum of the parts. So like the simplest example of that is this phenomena of a friend being a friend. So we would call that triadic closure. That's among three vertices, so three nodes, and if they're all connected with a positively valence connection like a friendship, the idea is that because of the reinforcement there, the value of a triad like that is actually more than just the sum of the dyads. It's stronger in that respect. So there's a whole lot to be done on and with network theory. There's large literature on just describing networks, and this is how most people first get into networks. This is like the equivalent of learning what a mean and standard deviation are in the network world. And I'm going to skip right over this because we don't have much time. But just know that that exists out there, all sorts of measures of centrality, diameter, clustering. And that leads into a big literature on communities in networks and inductively finding communities. This is a huge literature, especially in math and physics, looking for communities in networks, how stable the networks are, how we would sample them. The one we're going to focus on today is inference. So how do we do deductive hypothesis testing in the case of networks? So do something very similar to a regression and make a inference that's very similar to a regression like inference when we have network data. There's a lot to be done on prediction, on structure, action, diffusion, the list goes on. So this is a really, really big area, and we're going to talk very briefly today about one tiny sliver of it. So don't think that this is by any means the be all and end all of what network analysis is. This is a tiny sliver of a much bigger thing, and we're only covering it briefly. So with that, I'm going to shift our focus away from what networks are to how to do inference on networks. And all of these things are important and valuable, and other than inference, I'm not going to talk about any of them anymore, just for the sake of time. So let's focus in on inference and ask the question, how do we do deductive hypothesis testing when we have network data, rather than the sort of data that we're used to working with in the regression framework? And the first point that I want to make about that is that we need techniques that are designed for network analysis to do this. What we cannot do is just use the regression framework that we all know and love. And I'll show you why we can't do that. So that's the section that I call the dangers of mistreating network data. So the first argument that I want to make is that relational data are network data almost always. So it very rarely makes sense to think of data that are about the relationships between units, between actors, as being distinct from network data. Because a network is going to rise anytime actors can have multiple relationships, that they can influence each other, and they interact in any sort of closed or pseudo-closed system. So that's more or less anytime the relationship is the unit of analysis. This is going to be true. And so we can only think about relations being not a network when some of these things are violated. So for example, multiple relationships is the easiest one to think about. If actors are restricted to having only one relationship, that can then form a sort of independence where we don't in fact have a network. So instead of talking about friendship ties, let's think about marriage ties, right? In most places and most cultures, you're not allowed to have more than one spouse. So a set of spouses where the relationship is spousal only, so not just anyone you know or anyone you're related to, but only spousal relationships, that will not be a network because it's just going to be a set of a whole bunch of connected dyads that aren't connected to each other. So there's not going to be any structure there. But when multiple relationships are allowed in other contexts like friendship or trade or conflict or internet links or whatever, right? When you can have multiple relationships, then complex networks naturally form out of that. So my first argument is that anytime the relationship is the unit of analysis and we're interested in the relationship between things, this will usually produce network data. And we need to treat it as network data. So why do we need to treat it as network data? The reason substantively in a nutshell is that those complex patterns of interconnection that we've now seen some examples of in the plots, they form a dependent structure that's endemic to the network. And traditional statistics like regression can't actually model those sort of complex interdependencies. And you may say, well, that's not really a problem because maybe I'm not actually interested in the structure of the network. I'm really just interested in understanding how some vertex level or relationship level thing affects a relationship level outcome. That still isn't really licensed to just ignore those complex interdependencies, because if we don't model them, so if we fail to model them, it's a form of omitted variable bias. So not only will it play havoc with your standard errors, but it also can falsely attribute explanatory power to covariates, and it really raises the risk of faulty inference. So we risk making an analytical mistake and coming to an incorrect conclusion when we don't account for these things, even if we're not primarily interested in it. But I would also argue that understanding these structures represents a new frontier theoretically, and a big opportunity theoretically to create theories that address those structures and then test them, which most people have not done about most things in political science, since networks are relatively new and not super popular throughout the discipline. So it's a target-rich environment for theoretical innovation as well as testing. And so let me break down these reasons in more detail. So the core problem, and probably the biggest reason why we would not want to do regression on network data, is the following. So all likelihood models follow this form, basically. So this is a very general way of writing regression. This could be a Gaussian linear model, it could be logit, could be probit, could be a Poisson model, whatever. Right? We're taking the product over a whole bunch of conditional probabilities. Right? So the probability of yi conditional on some set of regressors and the parameters, right? Where f is the probability density. So that's whatever distribution you're using. So if it's a linear model, that would be a Gaussian distribution. And the part I want to focus on is this product, right? We get the joint likelihood by taking the product over all of these independent yi's that are conditionally dependent only on xi. And what this means is that if I'm I, right, my response, my yi, has nothing to do with your response if you're j, right? So yj does not figure into this equation at all, and in fact can't. So we're assuming that the units are independent. So the IID assumption we always hear is independent and identically distributed. The identically distributed bit comes from here, right, where we're assuming the same distribution from all of them. But the part that's important with respect to networks is the independent bit. So we need to assume that they're independent from one another in order to be able to take the product over all of them and have that be a meaningful joint likelihood. And when that's not true, like in a network context where you have observations that are related to each other, then this is violated. And that means that you can take the product, like mathematically you can, the software won't stop you, but you won't have a joint likelihood. So you'll have some arbitrary amount of bias in that likelihood. And so you will get a number, but it won't be the right number. And so that's the main reason why we don't want to do regression on network data. Yeah. Does that make sense?
Yes.
That's maybe a little bit abstract. Yeah. Right. So what does it mean to say that my response is independent from someone else's? if we think in political science about voting behavior, that's something that we often think about. What candidate do you vote for? This assumption, this independence assumption, implies that who I vote for is independent of who anyone else votes for. It's conditioned only on attributes that are related to me. So my age, my education, my income. Those things affect who I vote for, but they're all things about me affecting my response, not anything about anyone else's behavior affecting my response. But is that a realistic assumption when we're thinking about voting behavior? Probably not. My friends and family relations affect who I vote for, right? So in all likelihood, had I voted for Donald Trump in the last election, I would not be married anymore, right? So my relationship with my wife strongly affects my voting behavior in a way that will break regression. And will mean that we get something by taking this product, but it's not a joint likelihood, and we shouldn't trust the results that come from that. Does that make sense intuitively and mathematically?
Any questions?
Yeah.
I have one follow-up
Yeah.
comment from an early example by Camilla about transatlantic drug. I think she's asking, and if tracking counterfeit malaria medication into sub-Saharan Africa from transatlantic trade with Asia and Europe. So that may be something she is further interested in. So maybe we can use that as like illustration, and then see how that could be applied. And another comment is from Thang, and she said the voting example makes sense, and yeah, I think so. That is based on a big assumption. So things are independent, but because we're doing traditional retrain is a regression person. Everybody knows how to do the regression, but assuming that every case is independent, and so that is a big assumption. And when it comes to knowing that everything could be network, yeah, then
Yeah, so regression works very well for what it's designed to do, right? If we're looking at voting behavior and we have a sample of 1,000 people randomly drawn from across the country, it's astronomically unlikely that any of them know each other. So it's reasonable then to think that their responses are going to be independent from one another. Like that makes perfect sense in a survey sampling case. It's the sort of thing that regression was designed for, and it works very well in that situation. But if we have this sort of deeper contextual knowledge of what's going on within a network, then it no longer makes sense to treat observations as independent that way.
No, I saw this. Yeah, go ahead, Peter.
Yeah, take that. But here's just a question. Taking the voting example, and then what if we include that the relationship? Say, if you have a question and ask people that your friends or families affect your decision of who to vote, and then if we use this as one of the covariate, does that help? Still use the regression idea.
It can help a bit. So what you're talking about now are ego nets, right? Where we're asking each respondent about who their friends are. And a couple issues come up with that, right? So if you ask me to name all my friends and name their preferred candidate, I'm probably going to get at least some proportion of that wrong, right? So my perception of who someone supports for a given election may not be who they actually support. So there may be some measurement error in there. And while that does bring you in the right direction, it also doesn't completely solve the problem, because it doesn't allow for the fact that maybe some of my friends know each other. And so then you have reinforcement within that. So if you have a closed triangle there, where two of my friends are also friends with each other, that's something that you just can't model in the regression framework, or at least really not well. There's, okay, that's not entirely fair. There are some models like the AME and the latent space model that do highly parameterized attempts at capturing that sort of thing by plotting everyone into a latent space where their proximity is proportional to their probability of tying. But that's already now pretty far outside the context of regular regression. So the regular regression framework can't deal with that sort of thing. And certainly can't do deductive hypothesis testing on it, which is an additional limitation. To sort of give a deeper substantive context to this, one of the examples that was motivating for me when I started getting into network analysis, I started really appreciating network analysis when I was early in grad school, and I was taking a bunch of classes on international relations, which at the time was my substantive focus, and I've since sort of moved away from. But I was taking that as well as a bunch of methodology classes, so I was learning about regression. At the same time, I was learning about international relations. And one of the things that's really common in the international relations literature is to do, let's say if we're studying conflict, it's to do a logistic regression on whether two states, so a dyad, whether they go to war with each other, and do a regression just like this. So a logistic regression model where that's the Bernoulli distribution. Yeah, so we're conditioning the probability of war between two countries on the attributes of those two countries, like trade, regime type, GDP, that sort of thing. And then it struck me that it's like, okay, so what does this independence assumption mean in the context of international conflict? That means very specifically that the British declaration of war on Germany in 1939 had nothing whatsoever to do with Germany's invasion of Poland, which is laughably false, right? Like that is the thing that started World War II. These were not independent events by any stretch, but the regression argues that they are. It requires that they are. And a former grad student of mine, Ben Campbell, he did a literature search, an extensive one at one point, and identified literally thousands of published articles in political science that make that exact assumption about international conflict, even though no one would actually claim that substantively. So the model is forcing assumptions on us that we wouldn't ever want from a substantive perspective, and that are obviously false, right? So that's also a theoretical problem, not just a mathematical problem.
Yeah. Okay.
Yeah, so that's the main reason why we want to not do regression on network data. But I've got two others that I want to really quickly cover before we start getting into the ERGM, and I need to increase my pace a little bit if we're going to be done in 45 minutes.
Yes, yes.
Okay. So there is a problem with levels of analysis. And I'm going to pick on IR a little bit because levels of analysis are a big deal in the international relations literature. Like there's the state level, the dyad level, and the system level. But this is silly because we're talking about the same system. Like these are all parts of the same system. And why wouldn't we treat them holistically? Like things at the dyad level affect things at the state level. Things at the system level affect things at the state level. State level stuff affects dyads and systems, and it's all happening at the same time. So cutting it into different distinct levels of analysis that theories about these things are often mutually exclusive even, really doesn't make sense from a theoretical perspective and is actually counterproductive. But people have done it because that's what regression can accommodate. You get one level of analysis in a regression, and so people have picked levels of analysis and made a theory about that. But that's like a drunkard search, right? That's like looking for your keys under the lamplight, not because that's where you thought you lost them, but because that's the only place you can see. And that's not good from a science development perspective. And then very lastly, there's this issue of data multiplication. So again, picking on IR and those logit models of conflict that I was just talking about. If there are 150 actors in the system, there are over 11,000 dyads at that 1 year, so that one point in time. And it's common to do dyads between 1816 and 2010 or 2020. And now we're talking about millions of dyads. So what is N, right? If you're doing a regression where you have over 2 million dyads, if you, or more than 4 million dyads, if you're talking about a directed network, since p-values are at least in large part a measure of sample size, like if you don't get 3 stars, you should be embarrassed, right? And that's also really bad from a science perspective, right? We don't want to set ourselves up in a situation where we're getting statistically significant results on substantively meaningless effects, right? So that's an issue. Here's a plot of how our number of observations increases as the number of nodes in the system increase. Yes, it is nonlinear. And it also doesn't make sense, right? Like if you look at the correlates of war data set, again, picking on IR, so sorry to do that. I didn't mean this to be an IR workshop. But the correlates of war data set treats World Wars I and II as 567 completely independent dyadic wars. So they only get 2 names, but they're actually 567 wars. And that doesn't make sense. Right, that means World Wars I and II are almost half of the wars that have existed since 1816. And like this just doesn't make sense. So it's a weird way to treat the data when we try to force this into a regression context. And it causes all sorts of problems theoretically and also empirically. So that was my pitch for why we should never, ever, ever do regression when we have network data. When we have network data, we need a model designed to deal with network data. There are several of them. And the one that I'm going to introduce today is one of the more powerful and more popular ones called the ERGM. And that's sort of our pivot point into breaking out the specific math and application of the ERGM. But before I do that, are there any questions about any of the stuff we've talked about so far? What is a network, designing network studies, why you don't want to do regression on network data, or any of that?
Anyone? Okay, I think maybe
No.
Save questions for the end, to the end.
Okay.
Yeah, please go ahead.
Okay, so if there are no questions, then let's get into the ERGM itself. So the canonical citation for the ERGM is Wasserman Pattison, 1996. Their Psychometrica article laid out the concept of what's now known as the ERGM. They called it P-star at the time, but the terminology evolved a little bit since then. So they laid out the original logic to what an ERGM is, and then there's been a lot of development since then. And in some shameless self-promotion, the ERGM entered political science with this article that Bruce and I wrote back in 2011. And recently, technically just this year, though it actually came out at the end of 2021, we wrote a book called Inferential Network Analysis. That is the only text I'm aware of that is dedicated entirely to inferential models of network analysis, including the ERGM, but including some others as well. So
I checked in the UTD library. We had a copy, but it has been checked out through interlibrary loan. So, so
cool.
maybe I need to get it reserved. Don't fight to keep the book, and we need to share it to everyone.
Yeah, so basically, also shameless self-promotion, right? If you find this workshop interesting and it's something that you want to go deeper into, I personally think this is the best resource to get started with because it's basically my networks class turned into a book. Yeah, that's at least how I approach the subject. So that's a resource for learning more if you find that you want to learn more after this. And it also has a ton of real data examples and R code that come along with it. So you get it not only theoretically, but how to do it.
Mhm.
Okay, so let's do the ERGM. We need a little bit more notation than we had before, but some of it's going to be familiar, right? So N is, or big N is the network, small n is the number of nodes. For the moment, and actually for this entire workshop, we're going to assume that edges are binary, meaning that a connection's either on or off, like we're friends or we're not. So we're not going to do this in a weighted way. We're also not going to do it in a temporal way. Both of those extensions exist, but we're going to talk about the basic ERGM, which assumes a single network and edges that are either on or off. So that's a limitation of what I'm going to show you, but just know that that's not actually a limitation in practice anymore. That's just a limitation of the most basic intro model. Okay, so we're assuming that for the time being. And we need to introduce the concept of fancy n. So fancy n is the set of all possible permutations of n, so of the network n. And what I mean by that is it's every way that you could configure the network with the same number of nodes. So let's say we have 100 nodes in our network. Fancy n is the collection of all possible permutations of that, from completely empty to completely complete and everything in between. So that's a network with only one edge among those 100. And then also with one edge among those 100, but between different vertices. And again, between different vertices. So every possible edge, every possible network that has only one edge, every possible network that has two edges, every one that has three. This is big. It's 2 raised to the power of n choose 2, is how many permutations are in fancy n. Does that make sense as this really big collection of all possible networks that could exist with the same number of nodes? With all possible number of edges. So from totally empty to totally complete, and every permutation of everything in between. It's literally every.
Do you estimate the correlations of these different fancy n permutations? Are they taking into account correlated ones?
Yeah, they'll probably be correlated with each other in some cases, right? But this is literally just every way that we could configure edges with the same 100 nodes. So this is a really, 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 really big collection. Like imagine that every network or every possible permutation is a tile on a floor. This is a floor that would feel infinitely large if you looked at it, right? It would be huge, even with a pretty small number of vertices. Like, yeah, with 10 vertices, we're already talking, I think, about over 1 trillion combinations, right? Because yeah, 2 to the power of n choose 2. Yeah, so what this gives us, though, is conceptually the opportunity to say, okay, let's have our modeling objective for the ERGM be recovering a probability. So what's the probability of the network that we did observe over the networks that we could have observed? So what's the probability of n, the network we did observe, over all of these networks that we could have observed? And if you have a background in physics, you'll notice that this is actually really similar to the concept of entropy. So it's an entropy model of networks. Okay, so that is that with fancy n, and here is the ERGM itself. So this is the mathematical structure of the model, and let's break it down in parts. So the outcome, the thing that we're recovering, is the probability of the network that we observed, and a set of parameters. So the parameters, the coefficients, will look very similar to regression coefficients. The end result of this will be a table that looks more or less like a regression table. But as you can see from this, this is not regression, right? This is really different than this. So there's no product, there's no independence assumptions. But let's break it down piece by piece. Here are the parameters, right? Those are the coefficients that we're going to estimate. We're taking their transpose, which I'm denoting here with a prime rather than a t, because when eventually we would extend this to temporal models, having it indexed by t gets confusing, and yeah, you don't want to be indexing by t and have people think you're taking a transpose, right? So the prime here is indicating transpose. And then we have h of n. And what h of n is a vector of statistics that are computed on the network. And I'll talk in great detail about what that means in just a second. But it's the same length as the number of parameters. So we're estimating a parameter, a coefficient, for every summary statistic that we compute on the network. And we're taking the exponent of that, which is why it's called an exponential random graph model. And in the denominator, we have the same exact thing, except we're dealing with n star, where n star is an element of fancy n. And then we sum over all of the elements of fancy n. So fancy n, again, is the collection of all possible permutations of the network, and n star is any one given permutation of that network. And so you can see from this that what we're talking about is in the denominator, we're getting this value, so the parameter and the h of n, for every possible permutation of the network. And then in the numerator, we have the network that we actually observe. So that's how we get the probability of the network we observe over the networks that we could have observed. And in fact, the denominator is just a normalizer, but this is the source of much consternation and difficulty when it comes to estimation, because fancy n is so big that it's usually going to be impossible for all but the most trivially small networks. It's going to be impossible to actually compute this denominator, so we need to approximate it. And approximating that denominator is one of the big computational challenges that come with this sort of model, and also a reason for some computational instability that also often occurs in this model. And I'll talk about that later. But that's conceptually what's going on here. Does that make sense, except for the fact that we haven't talked about what h of n is and what actually goes into h of n? So I know I haven't covered that bit, but does the overall structure of the ERGM make sense?
Yeah.
Cool.
Yeah, can I jump in a little bit?
Yeah, of course.
Go ahead.
Your question is about the function, and you just mentioned that maybe the previous page that says the diet, right? I mean binary, either yes or no. There's a relationship or not, and then does this function also include the strength, the magnitude of the relationship? Say we have stronger tie, a weaker tie, and is that considered in this?
No. So in fact, you can see from this equation just why it wouldn't work if we had a continuous value, right? So the basic ERGM is only for connections that are on or off, because fancy n is already really, really big when we're just taking 2 to the n choose 2 with observations that are on or off. But if we had a continuous value, so something truly continuous is infinitely granular, right? Or can be infinitely small or infinitely large, we no longer have a finite sum in the denominator when that happens. And the basic model will no longer work when we have that sort of weighted connection. That doesn't mean that it's impossible. It means we need to use a different flavor of an ERGM class model called a generalized ERGM. which takes advantage of the fact that this denominator, it doesn't actually need to be finite. Really, all it needs to be is convergent. And so we can use integration to assure the convergent nature of the denominator and still have a model that is well defined. So that's an extension called the generalized ERGM, but we won't have much time to get into that today, unfortunately. It's close to my heart because I helped develop it. But unfortunately, we're not going to actually get there.
Fine. So that means that we have to look into your book, right?
Yeah, exactly. Good advertisement for the book. There's a string of papers that I wrote with Bruce and James Wilson and Shankar Bahmidi that unpack the estimation and theoretical properties of that. So if you're interested in that, you can look up the source papers on my CV, or we do kind of a high-level coverage of it on the book.
All right.
Yeah. So the extension exists, but that is something that is limiting the most basic model. And also you can see that this isn't temporal, right? Because we only have one n here rather than a whole time series of n's. But we can also extend this to the temporal case without too much difficulty. Okay, so that's the basic structure of the ERGM, except I have this sort of teaser here where I say H can capture virtually any form of interdependence among the edges and covariates. So what does that mean? Because H of n is actually the powerhouse of the ERGM. It's what makes it such a powerful model. And so we're going to need to unpack that. But before we unpack that, there are a couple things to note about the basic structure of the ERGM. Is you notice obviously that it doesn't involve getting a joint likelihood by taking a product over a bunch of IID data. The computational trick here, or the conceptual trick, is really to treat the network as a single multivariate observation, like it's a draw from a bigger conceptual multivariate distribution. And so in that sense, we're basically doing n of 1 inference. So looking at the network that we drew from the set of networks that we could have drawn. And that's the conceptual trick as to how we do that without IID assumptions. Yeah. So since we no longer have IID assumptions, we can capture almost arbitrary forms of complexity. So that there are some limits on the complexity of the structures that we can model, but they're relatively weak. And we'll understand those better as we unpack the H of n. And lastly, though, before we get into H of n, all models have assumptions, and we need to be transparent about that, right? So when we first learn regression, everyone has to memorize, yes, we assume IID, independent and identically distributed, but no one really worries about what that means, though they should. So I want to highlight some of the assumptions that the ERGM makes and encourage you to worry about them or not as you see appropriate. So the first is that given a set of network statistics that will compute in H of n, we're assuming that there's an equal probability of observing any two networks that have the same value of those statistics. And this is the ERGM equivalent of the assumption that we usually make in regression that a model is completely incorrectly specified. But what it means is, if we think about what it means for any two networks with the same value of a statistic to be equal probable, let's imagine a really simple, small example network that has only a single 2 star. So a 2 star is a connection from I to J to K, where J is the focal dyad. So J is connected to I and K. If we have two networks of just 10 nodes that each only have 1 2 star, this assumption is saying that those networks have the same probabilities, right? Even if it's different nodes involved in the 2 stars and the two networks, they have the same probability of occurring. we can understand the intuition for that by asking, well, if they didn't have the same probability of occurring, let's say this network was more likely than this network, even though they only have the same 2-star, that means that something is making that network more likely than the other, and that something is not something we're modeling, which would mean that the model is not completely and correctly specified, right? So that's what that assumption translates into. Okay, so that's assumption number one. Assumption number two is that the observed network exhibits the average values of those statistics that we're computing over the ones that could have been observed. This identifies the parameters, so it's a necessary assumption, but it's not a different assumption conceptually than the one that we make when we do regression, that says that the average relationships in a data set are representative of the population, right? That's the sort of sample to inference, or I'm sorry, sample to population inference that we're making. And we're doing the same thing with the network. So we're essentially assuming that the network is average of the networks that exist out in broader nature. Okay, so that's that. We've already talked about the limitations, actually. So the limitations of the basic model are that it is not temporal and it can't deal with weighted networks, but both of those are relaxable with the temporal ERGM and the generalized ERGM, respectively. So just because we're not covering that today, don't take that to mean that it's not possible. It is, we just don't have time to get into it. So we're only going to do the basic one. Okay, so now the really cool part, which is unpacking H of n. So H of n, like I said before, is a vector of statistics, summary statistics that are computed on the network. And it can include effects that are covariate effects at the node level, at the edge level, and also structural effects at the subgraph level. So it gives us a huge amount of flexibility in terms of what we include in the model, and allows the ERGM to be really powerful in that respect. Also integrating across levels of analysis. So how does it do it? It does it in the following way. So if we're thinking about covariates first, so let's start with exogenous covariates. We have some covariate X, which is like what you'll be used to seeing with regression analysis. We create the following statistic. We say Nij, so that's whether a dyad ij is on or off, right? So we're, if I'm I and you're j, that's going to be coded 1 if we have a relationship and 0 if we don't. And then xij is capturing the relational covariate that we have. So maybe that's, I don't know, we both like rock climbing or something like that. And so in the simplest case, this is going to be 0 or 1, and this will take on some value. So when this is 0, it just zeroes out, and we don't add value to the statistic. When this is 1, so we do have a relationship, then we're adding the value of that relationship on the exogenous covariate to the statistic. And we thus create a summary statistic that is the sum of those X values on the relationship for relationships that do exist. Does that make sense?
Mm-hmm.
So what you'll notice there is that this is naturally a dyad level thing, right? Because we're talking about Xij. But what if our covariate isn't measured at the dyad, so isn't measured at the relationship, but is measured at the individual level for any particular node? That's not actually a big problem. We just scale it up. So if Zi is something that's measured at the vertex level, so at the node level, then we can create a variable Xij that's just coded Zi for any covariate Z. So we can force this to look like a dyadic thing and do the same thing. So this is neat in that this one form of this statistic allows us to integrate covariates that are measured at the node level and also at the relationship level, which is more than you would have in any one given regression. That's like two different classes of regression analysis at two levels of analysis. And we can already integrate that in one just using this one equation, which is pretty neat. Okay, so that's how we deal with the exogenous covariates. Here are some of the ones that are commonly used, and this is actually the R calls that you would use to do it. So edge covariate is just a covariate that's measured on the edge. Dyad cov is the same thing, but directional. You can look at the absolute difference, and that can tell you about homophily. So if I have a value of some statistic, let's say my income, and the absolute difference with my friends is small, that would mean that I tend to form friendships with people who have similar incomes to me, which we know from friendship studies is basically true, right? People mostly form relationships within their sort of primary socioeconomic class, or that tends to be a form of homophily that draws people together. So we can measure it that way. And there are a bunch of other of these, right? So we can do node matching to capture homophily. We can capture popularity. We can capture sociality. So popularity is the tendency to form a lot of outgoing friendships. Sociality, or I'm sorry, that's opposite. So sociality is forming a lot of outgoing friendships, and popularity is receiving a lot of incoming friendships, for example. And there's a lot we can do with this. But the really, really, really cool part is how do we account for network structure? And so let's think about the simplest network structure that's endogenous to the network that we can capture through H as well. Let's think about reciprocity. So reciprocity can be specified like this. We can draw a picture of it, right? If I'm I and you're J, I have a relationship with you, you have a relationship with me, or I do you a favor, you do me a favor. And we can write that simply as Nij, which is this connection from I to J, times Nji, which is that connection from J to I. And so when both of those are present, this is going to be 1 and that's going to be 1. So the whole thing is going to be 1. If either of them were 0, then the whole thing would 0 out. And we're basically then just counting the number of reciprocal edges that exist in the network and calling that H sub R of N. And that's one example of an endogenous statistic that we can include in the H vector. But it's not the only one. So if we wanted popularity, this starts to look a little uglier, but it's the same thing, right? So you're popular if you receive a lot of ties. So if I is the focal dyad and Ji is a tie from J to I and Ki is a tie from K to I, right? And so that's looking at the popularity of I, the popularity of J, and the popularity of K on the subgraph of 3 here. And then we just sum all that up, right? So we can capture popularity that way. Sociality is just the opposite, that's sending ties. And we can even capture much more complicated structures like transitivity. And this is something that's really not possible to do in the regression framework, where we have I sending to J, J sending to K, and I sending to K. But we can write that pretty easily as Nij, which is there, Nik, which is there, and Njk, which is there. And so we're just taking the sum over all of those where I is not equal to J is equal to K. And so we can account for transitivities as well. So if we're in an environment where the friend of a friend tends to be a friend, like friendships or international alliances, we can now build that structure into our model. And so what is really neat and you're hopefully starting to notice is that we can integrate across multiple levels of analysis with the ERGM. So this is something on a subgraph of 3, we were just talking about reciprocity on a subgraph of 2, and then a whole bunch of effects that are measured at the relationship level and then at the individual level. So we're capturing a whole bunch of different levels of analysis, or at least they would have to be different levels of analysis if we were doing this as a regression, but the ERGM can do it all in one shot. And that I think is really cool. And we can even get fancier with things like edgewise shared partners. So if the focal edge is I and J, then we can count the number of shared partners that they have, or just the number of partners adjacent to a particular dyad, even if it's not connected. This is a common thing to do, especially putting geometric weights on these. It can help solve some of the computational problems that can occur with ERGMs that unfortunately we're not going to have a whole lot of time to talk about. That's what it looks like. It gets uglier. But the last, and I'm going to have to skip a couple things. Yeah, okay. So I think I can do this in 12 minutes. Okay, so the last thing that I want to really focus on, or actually the penultimate thing, is how to interpret the ERGM. There are actually several different ways that we can do it. So we can do it at several different levels. The most natural mathematically, and thus the easiest, is to do it at the network level, where the coefficient that we recover is going to tell us the relative likelihood of observing one more value of a statistic compared to one less. So that's denoted here as nj plus relative to nj minus. And so what that means is, like, if we're talking about reciprocity, that means observing one more reciprocal edge in the network compared to one less reciprocal edge in the network. And we can get the relative likelihood of one more reciprocal edge versus one less reciprocal edge by taking the exponent of the coefficient that we get. So we can exponentiate the coefficient, treat that as the relative likelihood of observing one more of whatever statistic we're talking about. And that's the easiest way to interpret the ERGM at the network level. But we can also get edge level probabilities for this. So we can back out the probability of a particular tie from I to J, conditional on the rest of the network. So that's what this means. So not IJ. So conditional on every other edge in the network. And this is a logit model of the parameters and what are called change statistics. The change statistic is a statistic that captures the change in the value when we toggle a particular edge from on to off. So if we have a connection from J to I already, and we're talking about the IJ edge, toggling from off to on gives us a change in the value of the reciprocity statistic of 1. So that would be the change statistic. And so basically we can do this. It would be annoying to do it by hand, but there's software that will just produce these probabilities for you. So another way to interpret the results is by looking at these edgewise probabilities. And you can actually even get fancier using something called blocked Gibbs sampling, which is a way to make conditional distributions. Don't worry about the math, we don't have time for that, but basically we can look at how expected values depend upon each other and how variance propagates through the network. So for example, we can do something like this, like produce a plot where we can show for any number of existing ties that exist, we can look at the relative probability of observing a new tie. And so, okay, for 3 ties, the probability of a new tie is somewhere around 0.2. And if you already have 5 ties, it's somewhere around 0.3. So you can make these sort of more detailed conditional dependence statements. These are a little bit annoying to make because you need to define what you're looking for and then back it out through simulation. But it is possible to do. It just takes a little bit more work. But if you are happy with your final analysis and are trying to make things nice and transparent to your readers, it's probably worth the effort. But admittedly, it won't just spit it out for you. Okay, And the very, very last thing before I try to show you a really quick software example is to think about posterior predictive checking. So goodness of fit is what it's called, or GOF for short. So what this is that we want to make sure that the model that we fit actually fits the network well, and that we're not missing something big. And we do that usually with box plots, which you'll be familiar with, right? Shows the median, the IQR, the outliers, and so on. But what we do is, because the ERGM is actually a joint distribution, it's really easy to sample from. So we can just sample a whole bunch of networks from the ERGM we specified and compute different statistics as box plots, and then plot the observed values of those statistics across them. So for example, if we're looking at minimum geodesic distance, which is the shortest path between any two points, so any two vertices in a network, the black line is the observed network that we have. So minimum geodesic distance at 1 degree is 0.3, and then it drops and drops and drops. But what we see is that the box plots that we're simulating from this ERGM do a okay job of capturing that, right? So we're fitting well here, we're missing low here, we're missing low here, but we're fitting well there and there. So it's okay, but it's not great. And this looks really bad, right? So that's just all over the place. And we would rather adjust our models so that this fits a bit better, these fit a whole lot better, and we can at least say we've improved our fit. So oftentimes we need to adjust things a little bit iteratively and try to achieve better fit. Okay, so that is the really high-level overview of what an ERGM is, how it works, how we specify it, and what it means. So in the remaining 6 minutes that we have, I'm going to back up and show you how to actually do one of these things. So this is using a little example data set that I believe was circulated to you all, so you should have this available. The first thing we do is we load up the network package. The network package is a package that has a lot of summary statistics in it, but it also creates network objects in R that other functions can interact with. So I'm going to set my working directory, which will be different for you than it is for me. I'm going to load up the two data sets that we have. One is an attribute data set, and one is the relational matrix. And I'm going to make a plot, which is, or first I'm going to make a network object, and then I'm going to make a plot, which will render here, though I already had it up. And that's the time to introduce the substance of this, which is, this is just a toy example. I don't know if anyone's seen the TV show Grey's Anatomy. I've actually not, which is kind of funny because this is my example. But I'm led to believe that in the show Grey's Anatomy, there are a lot of romantic hookups between the people working in this fictitious hospital. And that's what this network is capturing. So some guy named Gary Wiseman went through and coded up all the instances where a romantic connection was either shown or implied between two characters in the show. And this is the network that it produces. So we see that some actors like Karev are fairly central and have connections to a lot of other actors. Males are coded in blue, females in pink. And yeah, so we see some structure emerging here, and also some disconnected components from the main network. Question? Someone said yeah.
Any questions from Taiwan side?
Okay, so this is kind of like a silly example, but it's actually not really silly in terms of its substance. This is something that epidemiologists deal with often when they look at the spread of sexually transmitted infections. So this sort of network is something that people really deal with in the networks world. just not with a TV show. Okay, so I'm going to show you two ERGMs. One that is very simple and has only exogenous covariates, and then one that introduces some endogenous effects. But to break down how to do it, the command is relatively simple. The command is ERGM, and then you specify the outcome network, which is called hookups here. We make that predicted by edges. So in the networks world, edges is like the equivalent of an intercept. So we pretty much always want to have edges in our model because it's rare that you would want to specify a model that doesn't have an intercept, for example. And then this first model has just a bunch of exogenous covariate effects. So we're looking at the absolute difference in birth year, with the idea that people probably hook up within about their same age range, right? So looking at the absolute difference in birth year, it'll be small when people are of a similar age, and it'll be larger when there's bigger age discrepancy. We also look at the node covariate of birth year on its own. And the idea there is that younger people are probably more likely to engage in romantic hookups than older people, who are often in more stable relationships later in life. So we look at node match of their positions. So position is like what they do in the hospital. And what node matching is doing is saying that we expect a negative coefficient here. So we expect that people are less likely to hook up with people in their same working unit. So they're more likely to hook up across working units. So we would expect a negative coefficient from node matching on position. We would also expect from the social literature a positive effect on node matching on race. So people tend to hook up within their own racial groups. And we would node match on sex with difference equals true. So what that's doing, the difference equals true thing, is saying that people generally prefer to hook up with members of the opposite sex, which is true of heterosexual relationships, which are more common. And then also we're treating sex itself as a node factor. And what that is saying, or what that's allowing us to test, is the idea that one sex may prefer hookups more than others. So men are often thought to be more promiscuous than women, and that should capture that. Okay, so that's what the specification is doing. I'm going to run it. It runs really quickly because we don't have any exogenous effects. I'm going to compute the goodness of fit statistics and plot them. And while it's doing that, we can basically see that we do have some effects, right? So we have this expected effect for birth year, or I'm sorry, for the absolute difference in birth year. So that seems to be a thing. Birth year itself seems not to be a thing, which is probably more typical of Hollywood than the real world. But we also see effects for position and race, but then also not for node matching on sex or node factor sex, which is also probably more a Hollywood thing given the size of the sample. But that is what it is. And I know we're out of time, but the last thing I want to show you is a more fully featured ERGM that's going to take longer to run. And this is, by the way, really small MCMC burn-ins and sample size with small max iterations. Like you would crank all of that up if you were doing this as anything more than just a teaching example. But so we've got a lot of the stuff that we had in the first one, but we're adding some proper endogenous terms. So we're adding a endogenous term for degree equals 1. So what that means, degree is the number of connections you have. And so we're specifically looking at degree equals 1 to try to build in the tendency for monogamy. And then we're also building in GWDSP, which is the geometrically weighted dyad-wise shared partners. So the number of partners that are shared adjacent to any one particular set of people in the network. And this will capture cliquishness in the networks, or a tendency of the network to cluster, which it looked like might be happening when we made the network plot before. So still estimating, but it's almost done. Should run fast. If you do this with big data and many iterations, this can take hours and hours, and you might need to run it on a powerful cluster, because as I mentioned before, fancy N is big, and so even approximating it is computationally demanding. But yeah, so here's what we see. Basically, this is what we saw before, except for when we include this tendency for monogamy, it also then changes the coefficients we get for node match race and node match and node factor sex, or node match sex, and yeah. So that changes some of those things. And ignore this. This is basically a problem with the way the default graphics work, because it's trying to plot over a bunch of stuff that doesn't really exist there. But what you do see here is that now that we've added those endogenous effects, our goodness of fit statistics are fitting pretty well. Like we're doing a pretty good job of capturing this trend. We're missing a bit low here and a bit high here, but more or less getting the trend right, and that's looking pretty good. So yeah, we can be happy with the fit, and we can draw inference then based on this table of results. Okay, we're done. I know we're 3 minutes over time, so thank you for bearing with me. I'm, of course, happy to take any questions, but hopefully you were asking those as we were going along. Yeah, so happy to take any questions or comments.
I think we will take maybe a small number of questions, because I understand that Dr. Cranmer is beyond his bedtime, and looks like he has got some sleep.
I'm a morning person, so usually I'm in bed.
Yeah. Peter, do you have any questions on your side first?
You go ahead. Yeah, I'm collecting.
Yeah, I think on the US side, and if you have a question, please do that now. I think indeed this is only taking as Dr. Cranmer suggests, it's only a tip of the iceberg. There's a lot of materials actually, and this is a lot of really illuminating examples too. So I want to ask a quick question about computation. So you set up the measurement iteration. This is something. Will that limit, or is this something you generally set as 5, or some kind of convergence that this is usually arrive at a 5, or so how do you decide those parameters?
Yeah, so normally you would want this to be larger and basically to go until convergence. I capped it here just so that it would run relatively quickly while we were talking.
Okay.
And also I made these MCMC samples pretty small so that it would run quickly. If I were doing this for a research paper, I would bump that up at least to 20 here, and probably add at least 1 0 to each of these. But it would also
try it now.
Yeah, like it would. At that point, you would basically, get it started, go do something else for a while, and check back in later, because it would take a while. Yeah, so if you've ever seen Bayesian models, the MCMC, or the process of MCMC burn-in and sample size, MCMC diagnostics works basically the same way. So you would still worry about MCMC convergence in the same way you would in a Bayesian model.
Yeah.
And I know from your webpage that Jeff Gill, one of my advisors, has already talked to you guys about Bayes. So
Yeah,
so hopefully he covered that.
Yeah, and yeah, you notice that Jeff actually has been giving multiple talks and on data science, is also Bayesian. Now we have a question quickly, and from Thang, what should we consider if we think about including loops in our network? I think she's referring to something like a repeating and back and forth and I think would you elaborate a little bit more about the loops, what you're referring to in the network? Are you talking about reciprocity? Yeah.
Yes, sure. So again, my data set is about social media and Twitter specifically, and there's a lot of people in the network that they retweet themselves. So
Okay.
I'm not sure if I should include them in my social network analysis. I mean, in terms of like trying to understand the network, and also in terms of using the inferential network analysis as well. So I'm not sure like what factor I should consider if I want to include them or exclude the loops from my networks. Thank you.
Yeah, so to a good extent, that boils down to a substantive decision that you would need to make about whether retweeting yourself is a meaningful thing. If you think it is, then yeah, you would treat that as a loop, and that's no problem. Like this can accommodate loops. Yeah, the ERGM can do that without any trouble. Or you could come to the substantive conclusion that that's not a meaningful thing for a person to do. Once they've tweeted, retweeting themselves doesn't do much, perhaps. So you could exclude it on that ground, but it's mostly a substantive decision. The model can do either.
Okay. Thank you very much. That makes sense. Thank you.
Sure. Thank you.
Maybe we can accommodate a couple more questions, Peter. Do you have anyone? Or from
Okay. Here's a question. I'm not sure if it's a good question or not, but would you try? Because it talks about the data collection. Data collection, which means that through data, I mean, it could be collected through interview or survey data, right? And then define the population and design a questionnaire. So what data or what variables are the crucial variables to be collected, and that would affect in the end how you analyze the research question, right? So the question says about
that's really a substantive question, right? What variables are going to be essential to collect will depend entirely on what the substance of the problem is. So like the example I gave earlier about snowball sampling with heroin addicts, right? One of the things that obviously the main thing you want to know, the relational thing you want to know is who shares needles with whom. So you would ask people who they share their needles with. That's the network itself. But you would probably also want to ask a bunch of other questions about the person. From demographics to like how long they've been using heroin, how often they use it, so what their sort of daily intake rate is, whether they're HIV positive or not, whether they have hepatitis or not, and a bunch of things like that. Those would all be really relevant things for that sort of study. But what you should be gathering as the relationship and also as covariates is going to change dramatically depending on what we're talking about. So that's really substance driven.
Yeah, I think the question comes from one of the study, and he tries to measure. It's the organization studies on the network organizations. So some organizations, they have like the major. It's like a network organization, and then some some individual organization, and then they have like allies and some kinds of, and the organization form are like that, the network. So the question asks that if they can measure if I connected with one of the major organizations, so I can be more sustainable during the downtime, economic downtime. I think that's basically the question is about. And so the student asking that if they can apply this kind of concept to measure how the organization form can be more sustainable. Yeah, something like that. I'm not sure if you follow me. Yeah.
Yeah, maybe. So I'm not sure I completely get the research question, but if it sounds like you're interested in how certain organizations can make themselves more robust by who their partners are. And if that's the case, then yeah, there's actually a pretty decent sized literature and something Jared and I have written on. It has to do with how robust network structures are to attack or failure at the edge or the vertex level. So how stable the structure is when there's some disruption to it, some sort of shock to it. And so that could be something that you might want to study. I'm not sure if that's exactly what you were getting at there, but just a guess.
Yeah. Okay. Thank you. Yeah. Thank you. Can you share that literature at some point? Maybe you type down the literature you just mentioned.
Oh yeah.
The article.
That's a paper that Jared and I just recently published in Network Science.
Okay.
I forget the title. Jared, do you remember the title?
It's all right. I can look it up for them.
Yeah, and Jared also has a paper he wrote with Selena Wang that also looks at some network stability stuff with respect to node knockout. So that would also be worth checking out.
Okay. All right. Thank you.
I think I just got it from Google Scholar. This is something I think I can share with you to the chat box. And okay, I think this is a lot of work, and so this is already late, and I have a few other questions, particularly about computation and how this can relate to machine learning. But maybe we should consider inviting you back again sometime soon. So I think this is
quite well with machine learning, actually.
Yeah. So quick question, are you offering courses, short courses like ICPSR, XX, and or other short courses? Our students could be taking a lengthier class from you? Not the full semester though?
I'm not, but those courses do exist at I don't know if Essex is doing it, but ICPSR definitely does. And yeah, as far as I know, ICPSR actually has like a 2 mini course sequence that I think covers both sessions. I'm not completely sure about that though. So yeah, that's one opportunity. The Political Networks Conference also usually has some training workshops before the conference actually starts. So usually the day before is a workshop day. That's another opportunity. Yeah, I do teach a full semester networks class on this stuff. So I'll do that in spring, but as far as I know, I think you have to be an OSU student to enroll in it. Yeah.
Yep, I think this is good, and I think there are a lot of learning resources. I think maybe Jared can enlighten us a little bit, but because he'll be teaching more courses, and but I think at this point I would just have to wrap up and really give Skyler a big round of applause because of that, and this is really informative, a lot of materials. all the materials already uploaded to the website. Please download and then also the source, the articles you try to run the model. And thank you again, Dr. Cranmer. I understand this is really late for you now, and we cannot say thank you enough. But I really look forward to learning more from you in soon future, hopefully. And thank you again. And Peter.
Yeah, thank you so much for having me. Thank you all for your attention.
Yeah, thank you so much.
Hopefully it wasn't
Yeah,
too much.
also
I know
mine.
that was kind of like drinking from a fire hose there. I threw a lot at you guys in 2 hours. So, yeah.
Thank you.
Yeah.
All right.
Thank you.
All right.
Thank you for staying up so late. All right. And then
Okay.
I know with the time is so limited, so maybe in the future, Carl, and we may invite Skyler to come back and to share more with us. Yeah, thank you. Thank you for
Definitely,
staying up today.
All right. Thank you
thank you.
again, Skyler.
Oh,
Okay.
thank you.
Good night. Good night.
Yeah,
Before
appreciate
I let the audience go goodbye, please be reminded next week we have another big hitter coming to the colloquium. Patrick Brand is going to give a talk on the day point. I'm sorry. Let me pull that up, and maybe I can just share the screen. Then you can see that the next, it's called change point models. So Patrick and Dr. Brand developed this, and I think this is a really important, innovative model, way of modeling time series data. So please take advantage of this. And the time, however, sorry for the time change. Now we go back to 8 p.m. in the Central Time, but and in Taiwan side, we go back to 10 a.m. in the Taiwan side. Sorry for the convolutions because of the daylight saving. Now we are back to Standard Time. So please do not miss this very special talk. And Dr. Brand has prepared for this colloquium, even though he may give some presentation at UTD, but I think this is a talk he has been preparing a lot already, and readying for this special event for our colloquium. Please do not miss this. Please don't miss it. Please register and note the time and put in your calendar. And I look forward to seeing you all next week, next Thursday. All right.
Thank you. Thank you, Dr. Hall, for your announcement. And please stay tuned and come back, and I hope to see you all next week. Thank you.
All right. Okay.
Good night.
Thank you, Peter, again. Thank you all for
Yeah,
coming early. Yeah.